Okay, so today we are going to discuss about the solutions of Laplace equation. Okay, Laplace equation. Okay, so Laplace equation in general you can write grad square phi equals to 0. That means it's a homogeneous differential equation, homogeneous partial differential equation. That means in the absence of any external source, no external source, no external source. Okay, and you know the inhomogeneous version of this equation. That means in the presence of external source, uh, the corresponding electrodynamics or the corresponding dynamics is governed by the equation, namely Poisson equation, which is grad square phi equals to minus rho by epsilon. This is Poisson equation, and this is the inhomogeneous differential equation because in the presence of external source, the corresponding laws of physics become inhomogeneous. But for the time being, we shall restrict ourselves to solve the Laplace equation. That means the homogeneous differential equation. Okay. So this one, grad square phi equals to 0. Okay. This grad square operator, this is a partial differential operator. This is called the Laplacian operator. Okay. Laplacian operator. And in Cartesian coordinate, this grad square is equal to del 2 del x2 plus del 2 del y2 plus del 2 del z2, which is scalar. So Laplacian operator is basically a scalar operator. That's why we shall frequently we shall find this Laplacian operator within maximum of the laws of physics. Okay, because any laws of physics are generally invariant under any rotation or any type of transformation. So this operator is basically invariant because it is scalar operator. So due to this invariance property, in most of the laws of physics, basically which are written in differential form, we can find this operator, which is called the Laplacian operator. However, in Laplacian, the Laplacian operator in Cartesian coordinate takes the form this one. Okay. But we are interested to solve this equation in spherical polar coordinate. That means in spherical polar coordinate, grad square is equal to 1 by r square del del r of r square del del r plus 1 by r square sin theta del del theta of sin theta del del theta, and the phi portion r square sin square theta del 2 del phi 2. Okay. So for simplicity, we are choosing this one to be capital phi. Okay, so this one is capital phi, and this is the small phi, which is included in the coordinate. Okay, r theta phi. Okay. So following this form of the Laplacian operator, you can write as 1 by r square del del r of r square del phi by del r plus 1 by r square sin theta del del theta of sin theta del phi by del theta plus 1 by r square sin square theta del 2 phi by del phi 2 equals to 0. Okay. So amongst different processes to solve this equation, we are going to adopt the separation of variable method. That means this phi is the function of r, theta and phi. Okay. And at first we are going to split it in two different functions. One is the radial part. So suppose the radial part I am writing as r function of r, and the spherical harmonics portion. You know the spherical harmonics portion depends on theta phi. So this is angular part y, which is function of theta phi. Okay. And in the separation of variable method, you can put it in the original equation, and you can separate them in a very authentic way. So you can write, if you neglect this one, then you can write r square, suppose y, r square del r of r square del r by del r. Okay. This one plus this will be r by r square sin theta del theta of sin theta del y by del theta plus r by r square sin square theta del 2y by del phi 2 equals to 0. Okay. So r square can be taken as common, and you can divide by capital R capital Y. Then you can write 1 by r, then del r of r square del r by del r, okay, equals to minus 1 by y, 1 by sin theta del theta of sin theta del y by del theta plus 1 by sin square theta, okay, 1 by sin square theta del 2 y by del phi 2. Okay. So this portion is completely dependent on r only. So this is the radial portion, and this is completely dependent on theta phi, but they both are equal. So you can equate them with a constant, and this constant is, suppose I am taking it as k. Then effectively you will find two equations, two independent equations. One is the radial equation, and radial equation is again del r of r square of del r by del r, okay, minus k of r is equal to 0. This is the radial equation. Okay. Now you can solve it in different way. Suppose I am writing this is r square del 2r by del r2 plus 2r del r by del r minus kr equals to 0. So this one is the equation of the radial portion. Now you can solve it in a power series way. Suppose you are taking r is proportional to r to the power, suppose r to the power, you can say r to the power m. Okay, so this one is suppose r proportional to r to the power m. Then you have m into m minus 1 into r to the power m plus 2m into r to the power m minus k r to the power m is equal to 0. Okay. So here you can write m into m minus 1. If you take r to the power m to be common, then m into m minus 1 plus 2m, okay, plus 2m minus k is equal to 0. Then m square minus m plus 2m, that means m square plus m minus k is equal to 0. So effectively m will be minus 1 plus minus root over m square plus 4k by 2. Sorry, this one is wrong. This should be 1. Okay, the coefficient is 1. So 1 plus 4k minus 1 plus minus 1 plus 4k by 2. And here the trick is that if you choose k equals to l into l plus 1, say k equals to l into l plus 1, which is l is an integer, then you will find m equals to minus 1 plus minus root over 1 plus 4l square plus 4l by 2, which is 12 plus 1 er whole square. So minus 1 plus minus 12 plus 1 by 2. So there is two valid values for m for this case. One is m equals to, if you take positive, then m equals to 12 by 2, that means l. So m equals to l is a solution. And if you take the minus sign, then it will be minus l plus 1. Okay, so m will be minus l plus 1. Okay. So these two are the valid solution for this equation. So naturally, in power format or power series format, you have the solution r. R will be dependent on l because it's a polynomial like solution. So RL of R, it will be summation over L. Okay, summation over L, the linear combination of these two solutions. So AL R to the power L plus BL by R to the power L plus 1. Okay. So this is the solution of the radial part. Okay. And it is very, very interesting. I am choosing a trial solution. Generally, you choose the trial solution in terms of exponential, right? Okay. E to the power r or e to the power alpha, just like that. But here, we are going to in a different way, where I am choosing r to be the mth power of small r. And from this choice, we have found two valid outcomes. One is for m equal to l and another is for m equal to minus l plus 1. And we are taking the linear combination of these two solutions. So RL of R is equal to this one. Okay. Next, the angular part. Okay, so already we have found k is equal to l into l plus 1. Okay, so the angular portion now is very interesting, which is 1 by sine theta, 1 by sine theta, del theta of sine theta, del y by del theta, plus 1 by sin square theta del 2y del phi 2 equals to minus L into L plus 1 of y. Okay, so this equation I am writing to be in that way, plus L into L plus 1 y equals to 0. So this is precisely the angular portion, that means theta phi portion. Okay, but we need further separation of variable because y, this is function of theta phi. Okay, and it can be split into two parts. One is the theta portion, capital theta is function of theta, and phi, which I am choosing psi to be function of phi. Okay, now you can put this one in the equation, original equation for this separation of variable. Of course, this is phi 1 by sin theta. You can multiply by sin theta on the both side, so it will be sin theta. If you multiply sin square theta, then it will be sin theta y del del theta of sin theta. So of course, putting theta and psi, so you have psi sin theta del theta by del theta. Okay, plus theta del to theta, del to psi, basically del to psi by del phi 2 plus L into L plus 1 into sin square theta into theta psi equals to 0. Okay, I have to accommodate this within this very narrow region, but you have to realize it. Okay, so I am multiplying by sin square theta and then put this trial separation of variable. Okay, so again you can separate the independent equations like that way. Sin theta del del theta of sin theta del theta by del theta plus L into L plus 1 sin square theta, of course this is 1 by theta, equals to minus of 1 by psi del to psi by del phi 2. Okay, and these are mutually independent. This is completely dependent on theta, and this is completely dependent on phi, but they are equal. So you can choose, it is a constant, and for simplicity I am writing this is m square. Okay. So this is equal to m square. So at first I am focusing on the phi equation. The phi equation, which is del to psi by del phi 2 plus m square psi equals to 0, and this one will yield the solution a to the power im phi plus b to the power minus im phi, and here if you put the symmetry, which is psi of phi equals to psi of phi plus 2 phi, and from here you can only write this one, any one of this one, but I am choosing a to the power im phi. Okay, so we have the solution for angular phi equation. Then the most interesting part is the theta equation. So the theta equation will be like sin theta del del theta of sin theta del theta by del theta plus plus L into L plus 1 sin square theta minus m square of theta equals to 0. Okay. Now we need some coordinate transformation to solve this theta equation. Okay. For this one, I am choosing cos theta is x. Okay. So suppose del v by del theta, it will be del v by del x into del x by del theta. So what is del x by del theta? Which is minus sin theta. So minus sin theta del v by del x. Okay. So sin theta del v by del theta. Okay. So sin theta del v by del theta, it will be minus sin square theta del v by del x. So what is minus sin square theta, which will be 1 minus x square of del v by del x. So basically the operator is sin theta del del theta. This is identical to minus 1 minus x square del del x. So this is the transformation from theta to x. Okay. So if you put it here, then you have minus 1 minus x square del del x of minus 1 minus x square of del del x, that means del theta by del x. Okay. Then plus L into L plus 1 plus L into L plus 1 into 1 minus x square minus m square of theta equals to 0. So this minus and minus can be absorbed, and finally you can write del del x of 1 minus x square del theta by del x plus L into L plus 1 minus m square by 1 minus x square of theta equals to 0. So this equation seems very identical to the Legendre differential equation, except this portion. If you put m equal to 0, then you can restore the original Legendre differential equation, but it is not the original one. So in general, this is the associate Legendre polynomial. The solution theta will be p of lm of x, that is means p of lm of cos theta. Okay. So now for symmetric, so for spherically symmetric solution, you have m equal to 0, then theta, capital theta L, it will be PL0, that means actually PL, the original Legendre polynomial PL of cos theta. Okay. So the complete solution, if you put m equal to 0, then psi will it be 1. Okay. Or a, you can say. So in the order of 1 constant, because m equal to 0. So in this case, the complete solution phi r theta phi, it will be summation over L, okay, AL r to the power L plus BL by r to the power L plus 1 PL cos theta. Okay. So this one is the complete solution for the Laplace equation. Okay. of course it is the spherical symmetry solution. Okay, and this effect you can find this one for several examples, and also if you make the direct series solution in several cases, you will find such type of discrete summation of discrete solutions. Okay, for example, if you put some circular ring, uniform circular ring, and it is the x-axis which is z, axis which is z, the axis is along z-axis. Okay. So the radius is a, and you are going to find the potential phi here, which is 0 0 z. Okay, 0 0 z. And in spherical polar coordinate, it will be r. The value of r will be z. Okay, theta is actually 0 degree, and phi will also be 0 degree. Okay, so in this case, you can find this one. Okay, you can put it here, the value of all these thing, and you will find this one 0 0 z. Okay. Now the conventional way to find this phi z 0 0, it is integration lambda dl by root over z square plus a square. Okay. Of course, 1 by 4 pi epsilon naught should be there. This is the constant, of course. So this is q by 4 pi epsilon naught, the total charge, into 1 by z square plus a square whole to the power minus half. Okay. Now here you can choose two different cases. At first, you can choose z less than a. So if you choose z less than a, then this phi, it will be q by 4 pi epsilon naught into a. That means it will be 1 by 1 plus z square plus a square whole to the power minus half. Okay, this one. And sorry, this is plus half. Then q by 4 pi epsilon naught a 1 plus z square by a square whole to the power minus half. Okay, and you can make the binomial series for this one, and you will find the similar kind of effect. You will find the similar kind of effect here. Okay, so this is the direct evidences that the potential due to a extended charge distribution, it will the superposition of different poles, different discrete contributions, and of course you can also find it from the direct series solution. So you have two options for this one. One is for z less than a. Similarly, in the second case, if z greater than a, then it will be similar kind of operation, but it will be q by 4 pi epsilon naught z to be common. Then it will be 1 plus a square by z square whole to the power minus half. Okay, so it's all upon you to verify this one. Okay, verify this one following the binomial series. Okay, you can try yourself. Okay, and in the next class I shall verify this one, whether you could do or I have to do. But this is the procedure. You have to start from here. Then you can choose the binomial series expansion. Then you have such discrete effects. Okay, and from here, these are actually the boundary conditions, and from here you can fix the L and BL. Okay, L, BL are nothing, just constants, and these constants can be fixed from the given boundary condition. Okay. So this one.